Let's derive the expression for the current in the circuit, the impedance, and the phase angle, that is the angle found by the resultant voltage or the voltage and the resultant current. So this should be a circuit. The derivation starts by looking at individual resistance and the current. What is the relationship between them? That is, this is in phase. Here we have the current to be lagging. Here the current is leading. Right? So once we get that, from that we'll get the expression for your voltage, and from there we'll be able to compare with your ohmic equation, that is Ohm's law, and then get the impedance, right? So once we have the current and then the impedance, and then we'll be able to figure out the angle. So that's the agenda. So let's look at the math. First thing first, we have the series LCR circuit. We need to state that. And we need to write what kind of source we have. Voltage source is a function of time, and it's given by this. Now, voltage across each component is something that we need to look at. So your resistance will have a, if the current is I, the voltage across that will be V into, sorry, not V, I into R. So here the voltage and current are in phase. Agree? Next, we have VL, XL. Same thing. Here, what happens? Current lags voltage by half a radian. Next, incapacitance. Again, we have the same funda. But here, current leads the voltage by 90 degree or 90 or pi by 2 radian. Now, let's look at the phasor diagram. So this is where the entire thing summarizes. If this is the current at a moment of time, the voltage across the resistance will be in phase. The voltage across the capacitor will be lagging. That will be your VC. This is VR. With respect to the current, the voltage across the inductor will be leading. Is that straight? Looks straight. Okay. You guys, it's supposed to be straight, by the way, because 90 plus 90 is 180, right? So this is supposed to be straight. So this is VL. So we have to find the resulting voltage from this. We have to get back the expression for E. How will we do that? We have three vectors. We can add them. As simple as that. So first thing is VL and VC is simple to add. So in this case, it's the difference. So we'll end up something like this, I guess. Or let me make it a bit bigger. That is your VL minus VC in this case. So this is your vector. Vector, vector, vector. Now, since I know the difference, what should I do? Then I can take up this difference and the third vector and make use of what? I can make use of, what is this? Yes, your parallelogram of vector addition. So all I have to do is draw the diagonal from where the vectors are. So this would give us your resulting voltage. Okay, so the resulting voltage phasor E is obtained by adding the individual voltage phasors using the parallel law of vector addition, parallelogram law of vector addition. So that's what we have done. Now, this is the phase difference between the final voltage, that is your voltage source, and the current. Does it make sense? So we have to figure out in terms of magnitude what is E and phi. What is the actual value? Mathematically, how does it look like? This is also mathematical, but so this is part of the derivation actually. Next, once we have that, then we can figure out the magnitude of resulting vector. How? Same. So we know that we will be able to use from the diagram the magnitude of E is given by E square is equal to VR square plus VL minus VC the whole square. Right? Simple Pythagorean theorem. Since it's a right angle triangle, if not plus, you have the 2 AB cos of theta and all of that. Theta in this case is 90 degree. Right guys, so I hope you guys know all of the vector aspect properly. If not, it's not going to be easy. Next, this is equal to I square R square plus I square I'm taking out. This will be XL minus XC the whole square. Again, I'm jumping 1-2 step. We have to do that. And finally, E is equal to, right, I have I square common. So root of I square is I. Root of R square plus XL minus XC the whole square. Root actually, sorry, my bad. Not whole square. This is square. Root. Whole root. This is your expression for voltage and current, how they are related. Now, we have to figure out the impedance from this. How will we do that? Let's compare one with ohmic equation. So we have V is equal to I into R. So what is R in this case? Or sorry, yeah, Z. That's how we represent, right? So it will be R square plus XL minus XC the whole square. Whole to the power of 0.5. So how did we get this? Simple. We are comparing this particular, right, this particular equation with V is equal to I into R. So this R, I and I, V and V. So obviously R has to be equal to R dimensionally. So we are not using R as a representation. We are using Z as a representation, right? And that's your impedance. As simple as that. Is it not, guys? It's very simple and straightforward. Now, next we have to look at phasor angle. So how will we figure this out? This is also part of your derivation actually, but yeah, that is next part. Now we know that your voltage VR and your VL minus VC have to be perpendicular to each other, and this is your E, right? So say this is your resulting vector. This is our phi. How will you find out tan of phi? Simple, opposite by adjacent. So here, if we divide I with the numerator and denominator, if not, I just take I as common. So all of this will get cancelled and we have XL minus XC divided by R. Right? Does it make sense? So that is your angle between the current, because current is in line with VR. Okay, that's how we start off with. Since phasor I is always parallel to VR, right? The phase angle is the angle between VR and V and can be determined by the following. So basically this is, in place of V, we should be writing it as E. Please don't get confused, that is E. Again, with simple vector diagram, it's from this. So instead of using this, I just redrew. That's it, nothing else. You guys can use this. I just redrew. So if you look at this triangle, let me actually highlight that. This triangle, if I make use of that, I'll be able to find the phasor angle, the resulting angle. Okay, is it simple? Can you see that? Now, finally, the phasor diagram and your graph. Again, this can be done in the same thing, but yeah, I just want to keep it separate so that we are making things clear. So if this is your current, right? This represents your current. This will represent your, for example, voltage. So it can lead, it can be in phase, or it can lag the voltage with respect to current. So when you plot it on any graph, right, sinusoidal graph, if this is your voltage source, this is how it behaves, then either the current will lead or lag. So in our case, the diagram is showing lagging. So let's make it lag. So it would look something like this. It can be a bit better, but anyways. This is how it looks like. So that would be your current. Okay, let me revise the entire thing. I think I went a bit too technical. So what is that we have learned in this chapter? We got introduced to the idea of AC current, that it alternates every few seconds, every microsecond, actually every second, every whatever second you guys want to think of, it keeps changing. The magnitude and the direction keeps changing in some manner. Either this or that or both. Now, when you put this source across a resistor, it behaves normally. It's not a big deal. But when it comes to an inductor and capacitor, it behaves differently. Inductor, that is your coil, wire and all of that. We have seen that property because the wire, it induces an EMF and all of this. So when we turn it around, the effect is going to agglomerate. It will add up. It will accumulate. As a whole, what will happen? It will push back. Right? So that's the behavior of a inductor. While the capacitor, it's the behavior of the capacitor is like a storage space. So you store it, release it, store it, release it. So when we combine all of this in series, we get to use this particular setup in a different set of manner. To make use of that, of course, we need to understand how it behaves. How does the current behave with respect to the source voltage? So that's what we are doing in this particular video. So we started off looking at the source's voltage, and we looked at each component behavior individually. We put that on a phasor diagram, and we used our knowledge of vector addition. And we ended up having in this case, current is lagging the source of voltage source. Now, in terms of magnitude, how can we find out? Again, making use of the triangle of vector addition and all of that. So that particular formula we are using over here. And so finally, we end up with this particular expression. When we compare this with our ohmic equation, V is equal to I into R, you can see that the impedance, the resistance or the impedance resistance to your AC source, right? It turns out to be this particular expression. So that's your expression for impedance. Now I forgot one more thing over here. Expressing in terms of omega. So the frequency and all of that, right? Your AC source has certain frequency. So omega L minus 1 by omega C, the whole square. This is, by the way, C to the power of 0.5. Right? Then when it comes to phasor angle, it's the same thing whatever we did over there. Through that vector diagram, we'll be able to find the phasor angle. Simple. It's tan inverse of this particular expression actually. And finally, I have just the resulting phasor diagram and graph just for your knowledge sake to show you guys that the current in this case can lag behind the voltage. It can also overlap, that is, they can be in phase or lead as well. The current can lead. Okay, so this is the entire mathematics. And with this, we'll be able to understand what does tuning mean, the word tuning. When you tune your radio, what exactly happens, we'll be able to understand now.